Hey guys, welcome back to day 34. We're going to talk about aqueous reactions, classify them, and talk about molecular complete net ionic equations. First of our class of reactions we're going to talk about precipitation. We're talking about acid-base, gas evolution, and oxidation reduction. So what are these? Precipitation is where we form an insoluble solid product. Acid-base, where you have an acid plus a base, produce a salt, a compound, and water. Neutralization reactions. Gas, we produce a gas that bubbles out of solution. And oxidation reduction reactions are electron transfer reactions. And we'll dive more into all these soon. First, we need to talk about representing aqueous reactions. And there are three ways we're going to represent these aqueous reactions that these four that we talked about here. The first way we've been doing it is the molecular equation. And this is how we've been doing it. And all this is a chemical equation showing the complete neutral formulas for every compound in the reaction. These are our balanced chemical equations. The next type of reaction is the complete ionic equation. And some books will call it the detailed ionic equation. And this is a chemical equation showing all the species as they are actually present in solution. Such as sodium chloride does not exist as NaCl solid in solution. It exists as Na+, and that's a species, Cl-, and that's a species. HCl doesn't exist as HCl in solution. It exists as H+ or H3O+, and Cl-. So that's what we're talking about here. Then we have the net ionic equation. And the net ionic equation is a chemical equation showing only the species that actually change during the reaction. So that's the chemical change. The net ionic equation shows the chemical change. So when we talk about writing, when writing complete ionic complete, detailed ionic equations, or net ionic equations. We write all precipitates, gases, and weak electrolytes in the molecular form. Which is not ionized. So they're together in solution. So if you see an S, or in this case would be a solid, a G, these are aqueous, right? Also, if we see liquids, they're together as well, right? So let's dive now into the precipitation reactions, right? Precipitation reactions. So here's your solubility rules. What is a precipitation reaction again? We make an insoluble product. So typically, these are double replacement reactions where you have there. So AX, then going to BX, and ABZ going to AZ. One of them, it doesn't matter which one, will be solid. Everything else will be aqueous. All right, when we switch to ends partners. So this is your typical precipitation reaction where you have two things and you make an insoluble solid right here. Okay. Now here's the general solubility rules. And just, do you have to memorize these? Never. But it's good to know that group 1 and ammonium are always soluble. Nitrate and acetate are always soluble. So if you have a sodium salt, it's going to dissolve in water. If you have a potassium salt, it's going to dissolve in water. It's going to be aqueous. Nitrates are always going to be aqueous. And these are good to know. But now these are general trends. That doesn't mean that, I'm sure you can find an exception where something's very insoluble and it has, let's say, sodium in it. It doesn't dissolve that well in certain conditions and whatnot. It gets more complex. That's okay. These are the general rules. So the chlorides, the rest of the halogens, are pretty soluble except for silver 1, mercury 1, and lead 2. Sulfates are generally soluble with those exceptions. The hydroxides, sulfides, carbonates, phosphates are insoluble, but these are your exceptions. And that's all we would want to know about that. So let's do some examples. And by the way, when we do these with table 8.1 here, I just want you to use table 8.1 to figure out, is the product I'm going to make aqueous, solid, or not? Aqueous or solid. So let's do a couple examples of these net equations with some precipitation reactions. And so first, I'm going to show you that we have an S there. So we have aqueous, 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 solid. So is it balanced? Yes. So for A here, I have a balanced molecular equation. I have a balanced molecular equation. So now let's talk about the detailed or complete. Detailed or complete. Complete or detailed. So that's here. So what does silver nitrate do in water? I need to know, is it a strong electrolyte or not? That's basically it. Is it a strong electrolyte? Weak electrolytes or non-electrolytes are going to do the same thing for our equation. So is it a strong electrolyte? Well, how do I know? Is it a strong acid, a strong base, or a soluble salt? So I see silver nitrate. It's got a polyatomic ion of nitrate in it. It's ionic and aqueous, so it splits apart. That means I have 2 silver ions, because there's a 2 in front, and 2 nitrates. The sodium chromate, what does that do in water? Does it split apart or not? Is it a strong electrolyte? Well, ionic compound, ionic, and aqueous. So yes, it does split apart. So when sodium chromate goes into water, you get 2 Na plus ions floating around and 1 CrO4, 1 chromate floating around. Does sodium nitrate break apart in water? It's ionic and it's aqueous. So yes, there's a dissociation or ionization there. So we have 2 Na plus and 2 NO3 minus. Does silver chromate break apart? It's ionic, but it's solid, so it stays together as Ag2CrO4, and that, put in red here, is a solid. That's a solid. So for my net equation, my net ionic equation, what undergoes the chemical change? So if you look here, I have sodium on both sides. I also have nitrate on both sides. These are what we're going to call, all these are going to be called spectator ions. Spectator ions just watch. They don't do anything. They have to be there now because I can't just throw silver ion in solution. It can't just be silver ion. That doesn't work. I can't just have chromate in solution. All my ions, all my solutions are electrically neutral, and that's important. So these ions are there, they're spectator, they're just floating around. They don't do anything. So my complete ionic equation, or my net ionic equation would be 2 silver ion plus chromate going to silver chromate. So that's the actual reaction going on that we have. We make an insoluble solid product. We just switch dance partners. If, let's just say silver chromate was aqueous, there'd be no reaction here because everything would just be floating around independently. Let's try another one. So is this balanced? Yes, there's a 2 in front, should be balanced. What is the complete reaction here? Does sodium sulfate break apart in solution? And if it does, where does it break apart? Well, it's ionic and aqueous, so it breaks apart, and it's going to break apart with sodium and sulfate. So we get 2 Na plus and SO4, 2 minus. Hopefully, we have studied our polyatomic ions and know them well to recognize them. Lead 2 nitrate, ionic and aqueous. So we get lead 2 plus and 2 NO3 minus. So hopefully, again, those polyatomic ions, we got to know them. Lead 2 sulfate. Again, if you are not understanding how I'm saying why it's lead 2 sulfate, go back and rewatch the naming and practice naming again. Naming and writing formulas. It's very, very, very important skill. So lead 2 sulfate here is a solid, so it stays together. PbSO4 solid. Sodium nitrate, ionic and aqueous, so it breaks apart in solution. 2 NO3 minus. Where are my spectators? Who's watching? Who's watching? Well, what's my actual reaction? Highlight my solid there, so I need lead and sulfate. Lead and sulfate. Everything else is a spectator. So my complete ionic equation shows everything in solution. My net here will be sulfate plus lead 2 going to lead 2 sulfate. And there's my equations. Now, little note. All the answer keys will probably have PB2 plus first. They'll switch this around. And why would they switch this around? Does it matter? Ultimately, no. But by convention, we always put cation first, so it's always positive, negative. So it's always going to be positive ion, then negative ion, because it's positive ion, negative ion. That's why they do it. Would I be mad at you if you wrote it the other way? No. No, there's no lashes with wet noodles or anything like that. That's fine. Just let you know that the answer key is probably always going to flip them. You know, make lead first, lead 2 first, then sulfate. It's just the answer key doing it. Don't stress. You don't have to do it at this point. HCl. Well, does that break apart in solution? What is it? Well, it's a strong acid. So it does. H plus. Cl minus. NaOH. Does that break apart in solution? Well, it's a strong base and it's ionic and aqueous. So there's 2 reasons it separates. Na plus OH minus. NaCl, ionic and aqueous. Na plus Cl minus. Water, liquid. H2O liquid. What undergoes a chemical change here? Well, we make water. So that means hydroxide and H plus are what we need. And Na and Cl are just sitting there. So H plus, OH minus, going to water. And that's the complete and net ionic equation for hydrochloric acid and sodium hydroxide. Last one. This guy. Now, this guy in front, acetic acid, a lot of times we write acetic acid as HC2H3O2. Of course, it's still aqueous. And then NaC2H3O2 aqueous. Either way. So in Chem 2, a lot of times I write it the way it's typed. Chem 1, I always write it the way I wrote it. So it depends. It doesn't matter if you prefer it one way or the other, go ahead and do it that way. So acetic acid, does it break apart in solution? The answer is no. Why not? It's a weak acid. It's a weak acid. So that means it stays together. Does sodium hydroxide break apart? Yes. Yes, it does. It's ionic and aqueous and strong base. So we have Na plus and OH minus. Does sodium acetate break apart in solution? It's ionic and aqueous, so it does break apart. Does water break apart in solution? It's a liquid. No, it does not. Do I have any spectator ions? Yes, we do. Sodium is on both sides. That's it. That's my only spectator. Everything else is involved in the equation. So we have HC2H3O2 aqueous plus hydroxide going to C2H3O2 minus aqueous and water. And that's okay, right? That is okay. So that is net ionic equations with some precipitation reactions.